So we talked a little bit about aquifers. Aquifers are those rocks or piles of rocks or sediment or something underneath the ground that are capable of holding and transmitting water. And there are two fundamental kinds of aquifers, and they each have their own characteristics. These are called unconfined aquifers and confined aquifers. Unconfined aquifers you can think of sort of like your glass with ice in it. These are supposed to be ice cubes. Each one of those is an ice cube, and when you fill the cup with water or soda or whatever, right? You pour it in, it sinks to the bottom, and it starts filling in the pore spaces. And the more you pour in, the higher it goes, the higher the level, filling in, again, the pore spaces up to, say, here. So the pore spaces are filled with water, right? That's what the purple stuff is. And the more you add, the more water you add, the higher the level. If you were to put a straw in here, I don't have anything like that. If you put a straw in there and suck out the water, then of course the water level would drop. So the water level rises and falls depending on how much water you add or subtract. So that's essentially an unconfined aquifer, right? A confined aquifer is called a confined aquifer because if we can think of it more like maybe a water balloon. It's maybe that's not a great analogy, but here's a water balloon, and so you can have the confined aquifer can be completely filled with water. So this is supposed to be a balloon, and this is water in here, right? And the more water you add, the more the balloon swells. It stays completely filled with water. But if you subtract water, the aquifer, the balloon will contract on itself, but it still stays saturated with respect to water. There's still no airspace in there. It's just swelling or contracting. So let's think about geologically what a confined and unconfined aquifer looks like. Well, if you had a land surface, here's a land surface, and you have a bunch of soil up here at the top. So this is soil, and then down here somewhere you have your layers of rock, and we'll make them limestone. The geological symbol for limestone are just blocks like this. That's what these are supposed to be, like building blocks that are stacked on top of each other. All right, so this is limestone, but it could be any kind of rock. And as we know, there are pores in the soil and there are pores in the limestone. And so if it starts to rain and the water is soaking in, we can imagine that we are filling each one of these pores with water. And who knows, maybe the water table, the water rises in this, saturates all of the pores below this line, so that this is the water table here. This purple line is the water table. So everything, there's the little arrow. So everything below this purple line is characterized by pores being completely saturated with water. It's analogous to this part of the cup up here. And above this line, at least some of the pores are not saturated. They've got air in them. So this is the unsaturated zone above the water table, and the saturated zone below the water table. And if you get a really wet couple of months, then it starts raining more, then you're going to have more water soaking its way down. And just like adding more water to the glass, the water table is going to rise. So maybe after some time, I don't know if you can see this, but let's say the water table has now risen way up to here because it's been so wet, and you've saturated all of the pores between the old water table and the current water table. Okay, so the water table is free to rise and fall depending on how much rain you get. The confined aquifer is really quite different because it's confined. The aquifer is confined by geology. So here's our land surface again, and here's some soil on the top. And then let's say that we have a layer of shale. Shale is geologically shown as a series of short lines parallel to one another, like this. It's supposed to be sort of flat-lying clays. All right, so that's a shale. And shales are sort of characteristically known as having very, very low hydraulic conductivity. So the water can't flow through them very well, and so it acts as what's called an aquitard. It retards the flow of water. Aquitard, water flow. Water is retarded. The flow of water is retarded. And so water has a hard time getting from the soil in through the shale into the underlying rock. So let's put our limestone in here again. Limestone is these blocks. Limestones are sort of characteristically high porosity because they're soluble and they've got nice bedding planes and that sort of thing. And then we can put another shale down here as yet another aquitard. So we've got an aquitard at the top and an aquitard at the bottom. And as a result, what you can see is that this limestone aquifer in between is confined. It's restricted. So this would be let's see if I can write this out. This would be a confined aquifer here. So think of it a little bit like a water balloon. When it gets more water, maybe it wants to expand slightly. Solid rocks don't really expand and contract as much. Unconsolidated rocks are capable of doing that a little bit more. But if you are able to shove more water in here, and as a result, what happens is not that the water table changes its position, because the highest the water table really can go is the bottom of the shale, right? The water can't get through the shale, and so the water is sort of stuck in between these shale layers. But what you can do is you can build up the water pressure, and that's a really interesting phenomenon. So if we were to go back here and look at, see if I can get a different color. If we were to drill a well, let's say, down to here, call that well A, and drill that to well B, right? You can tell where the water would be, right? The water would go to right here in well A, and the water would go to right here in well B, right? Because that's where the water table is. But where would the water go if you drilled a well here, through the soil, through the shale, into the top of the limestone? Call that well A, and we'll do another one over here, through the soil, through the shale, into the top of the limestone over here at well B. Well, in a confined aquifer, what often happens is that because this water is under pressure, the water in the limestone, the water rises up in the well much higher than the limestone itself. Sometimes that water actually rises all the way up this high, above the land surface. When you get that situation, it doesn't have to do that, but that's kind of an unusual circumstance. It's called an artesian well. An artesian well is a well where the hydraulic head, remember, which is an elevation, is higher than the land surface elevation. So think about this back in the 1700s or 1800s. They didn't have electricity. They didn't have mechanical pumps, really, to speak of. They had to use wind turbines and very, very rudimentary pumps to get the water out of the ground. So if you were to drill or hand auger a well down through the soil and down through the shale, once you puncture the bottom layer of that shale into the limestone, what happens? The water comes rushing out under its own pressure all the way up above the land surface. So the water then is free to flow across the land surface to irrigate your crops or to provide drinking or whatever you want. So you don't need to pump it. And then when you're done with it, you just screw the lid back on the well and you hold the water in there. So if we were to do it over here, maybe the water comes up, I don't know, this high. Say it shoots up this high, there would be another artesian well. It could stop anywhere in here. The water could be at any height. But once you have the height of the water in wells, you can sort of connect the dots to create a plane. I'll draw it in 2 dimensions where it's just going to look like a line, right? But this line that I've just drawn is called the potentiometric surface, which sounds kind of complicated. It's really quite easy. The potentiometric surface, all the potentiometric surface is, it's the height that the water would rise to if you were to drill a well at any spot. So how high would the water rise if you drilled a well through the soil and through the shale at point C? It would rise to that height, right? How high would it rise if you drilled a well over here at point D? It would rise to that height. And so by looking at the shape of the potentiometric surface, this is drawn as a line, but it's actually, if you were to drill a third well out here, sort of not in a, in a triangle with A and B, you'd be able to define a planar surface rather than just a line. In any case, you can tell what direction the water's flowing now, right? Because it goes from high hydraulic head to low hydraulic head. So it's going to go from high hydraulic head at well A. It's going to be flowing to the right towards the lower hydraulic head at well B. So that's it. So that's a confined aquifer and an unconfined aquifer.